Hey everyone. So I've updated Andre Karpathy's Make More Baby Name generator to choose lotto numbers. So basically the baby name generator just trains on a list of baby names and then it outputs made up baby names which sound a little bit like names were made up by Dr. Seuss. And it's actually pretty good. So I'll take you through that and then I'll show you how I've updated it for the lotto numbers. So basically, Andre Karpathy gives a great course entitled Neural Network Zero to Hero, which he goes, and as part of the course, he builds this baby name generator and he builds it from scratch. He does everything from first principles. And this is the best tutorial series I've ever seen on neural networks. The paper he bases this on, is this Bengio paper, which is one of the early natural language papers for generating sentences. It's a fairly old paper, but what it does is it takes in, I guess, a sequence of words and then tries to predict the next word in the sequence, and then it takes that output word and adds it to the sequence and then takes in that sequence and tries to predict another word and so on to predict sentences. Now, the issue, I guess, for this is the input space. The dimension of the input space is the size of the vocabulary. Now, the average person's vocabulary is probably the typical vocabulary is probably 20,000 to 50,000 words. So we're going to have a huge input dimensional space, which might not be great. So what Andre's done is he's used baby names. So he's used his input space as letters. So he's got 26 letters and plus an ending and a start character, which is combined into one. So he's got a 27 dimensional input space. So this really cuts it down and makes the network easier to manage. And I guess for lotto numbers, where we might pick 44 or 48 numbers, then we're going to have like a 48 dimensional input space, or which will be quite easy to manage, especially in Python. So the first thing this network does is it defines an embedding. So an embedding is nothing that fancy. It's basically just a vector for each input word. So for each letter or number, we have a vector which is trained in which is the values of which we don't have to decide. We just randomize it, and it's trained through backpropagation. So because our input, we're using one hot encoding. So basically, we just have so say we've got 27 dimensions. We'll have it all zeros except for one where the index of the letter is. So say A might be the first index, then there will be a 1 at index 1. Or the dot, which is the start and end, might be the 0th index, then there'll be a 1 at that index and a 0 everywhere else. So that input will just choose an embedding. It means it's basically just an index for the embedding, which is a vector, and we have some freedom to define how many dimensions we use. So when I implement it, I'm using like 16 dimensions for that. But of course, if you're using vocabulary of 50,000 words, you might need to use like 100 dimensions or something a lot bigger. But for this network where we're using baby names or lotto numbers, we don't have to use such a large dimensional embedding. And then the next step is this multi-layer perceptron layer here, which has an activation function, and here he's used a hyperbolic tangent for an activation function. And when Andre builds up his network, I think he also uses hyperbolic tangent, but I've used a ReLU activation function, and then you can add another layer in here if you want. So in between this inputs, you can have as many layers as you like. I've used 2, and then the softmax output, which basically gives the confidence of each letter being next, or I guess in terms of a language model, whatever word in the vocabulary comes next, and then from there you can you can sample based on the distribution of these outputs to find whatever letter comes next. And I'll take you through all that. I'll take you through the code for that. So I'll take you through the code for the baby maker generator, and then I will, sorry, not baby maker, the baby name generator, and then I will show you how to update this for lotto numbers. So my code is a little bit I've rewritten Andre's code with the Keras library just here, just to make it a bit more concise. But Andre writes everything from scratch. So in his lessons, all his code is built up from scratch, and it's really good because he analyzes the network, he does a lot of diagnostics, and shows you how to build up everything. Even, writes a class for like batch normalization here, whereas in my code I've just used this is my whole, which I've just used this from the Keras library. So I'll take you through this from the beginning, and then I'll show you how I've updated it. Okay, so let's run this code. So first thing I do is I choose a seed for the random number, just so I don't get the same output every time, which is important if you're choosing lotto numbers. And then these are the libraries used. So this is the training data, which is in this names.txt. So basically this is provided by Andre, and it's all just a list of baby names that were downloaded from somewhere. I'm not sure, but there's like about 32,000 of them to train on. And then let's have a look. The length of so there's 32,033 baby names that we've got, or children's names. Okay, so now we extract our vocabulary. So our vocabulary just means that we get all the unique, all the unique elements, or all the unique letters. And I mean, this is obviously going to be A to Z, and plus we include an extra character here for start and end, which is a dot. But this kind of, it's more precise to do it from the data. So A is 1, B is 2, C is 3. So these indexes just make working with the data a little bit easier later on. Now our block size is our content length. So this is how many characters we're using to predict the next character. And at the moment I've got this set to 3, but you can change that and set it to different lengths. So that is like one of the hyperparameters. So we build up our set, and we build up our data set here, and then we use three data sets. So the X is the training, and Y is basically the X is the input and Y is the output. So X is what the network sees, and Y is what we want it to output, what we're trying to train it to. So Y is basically the correct response. So we have 3 of these sets. We have a training set, and we have a development set and a testing set. And the reason why we have 3 instead of 2, one for training and one for testing, is because the development set we use to set our hyperparameters, which are like the number of hidden nodes and the dimensionality of our embedding vectors, and of course something like the block size. So and then we use our XTE for testing, and we don't want to use the same set for testing and setting hyperparameters, otherwise we're fitting to that data. So let's have a look at what our training data looks like now. On the left is our input data, and on the right is what we want that output to be. So this is what we're trying to force it, when we calculate our gradient, what we're using in the loss function as the correct output, and this is what we're using as our input. So now let's set a seed, and then this is my model. So this is the model which I'm using from Keras. So the model is defined here. So first layer is just my embeddings. And the only thing that we're constrained on this model, not what we can't choose, is the vocab size. So the input has to be the vocab size, and also the output has to be the vocab size, because we've got 27 inputs, 26 letters plus the start and end character, and then we want to choose what's next from those 27. But everything else, the embedding dimension and the number of hidden layers, we can choose all that. So these are our hyperparameters. These chosen numbers are our hyperparameters, and I've just set the embedding dimension to 16, the number of hidden nodes in the first layer to 256, and in the second layer to 128. So let's build this, and it'll output what it is with this model summary. So I'm using an Atom compiler and a categorical cross entropy loss. And so basically what the cross entropy loss is it's the negative log of the probability of being correct, basically. So the probability that you've got that the output is correct, and the log of that, and we take the negative because we're trying to optimize it, is basically it's the expected value of the log of the probability that the network is correct, basically. So this model summary shows our network. So first layer is embedding, then I flatten out the embedding. So the embedding is 3 by 16 because I've got my block size is 3. So I've got one vector for each of those 3 letters that I'm inputting, or 3 numbers. And then I flatten that out into a 48 dimensional vector, just so I can input it into the multi-layer perceptron. I have to match this with this, and then I use batch normalization, which Andre goes into some detail on in his lectures, in his tutorials. And then I use dropout, which is for regularization, and then I have another multi-layer perceptron, and then another dropout, and then this is my output layer, my softmax output layer, which is defined here. So the activation function on this is a softmax, and then the activation on the hidden layers is a ReLU activation, but Andre uses a hyperbolic tangent for his activation, but I think the ReLU's the results are slightly better. So now we can fit the model here. We train the model and we use verbose equals 1, which shows the output. But before we train it, let's have a look at the loss on the testing data and the development data. So now the loss here is 3.2957 and 3.2955. And remember I said before, the cross entropy loss is basically the expectation of choosing the correct answer, basically. So if we've got 27 possible outcomes, 26 letters plus an ending and start character, and we've randomized it, then we would probably expect the probability of getting the letter correct to be 1 on 27. So let's have a look at that. Import math, and let's do negative math.log 1 on 27, and that's 3.2958, which is pretty close to this 3.2957. All right, so now let's train the network, and I'm going to actually stop the video while I'm training this. It shows you the output and everything just because it runs really slow when I'm running OBS. Okay, so it's finished. Okay, hey everyone. So it's finished running now, and we see the loss has gone down from around 3.3 to around 2.3. And if I run it for more epochs, for longer, then it will probably get a little bit, the loss will probably get a little bit less. So let's have a look at the loss on the training data, and then we'll redo the loss on the testing data. So the loss on the training data and the testing data is a little bit lower. So it's 2.17 and then 2.18 on the training data, on the testing data, 2.17 on the training data and 2.18 on the testing data. And the accuracy is around about 32%, and then 31% on the testing data, which isn't that great, but given that we're not making a hard decision, we're making a soft decision, that's actually quite good. All right, so now we've trained our network. The next step is to generate our baby names. So look at the output, and from that, how are we going to generate our baby names? So what we have to do, we have to sample from a distribution on the output, and I'll show you how that works, I guess, in an Excel file. So let's have a look at this. So this is, say, our input. Well, we start off with ... which is like 3 start characters, and say the first character predicted is an A, and then the input on our second round is ... A, and say the next character predicted is a B, and then we do .AB, and then so we just append the output basically to the input, and then our next output is an I. So say now at our next step, our output is ABI. So I've drawn out the probabilities here, just in there. So the next step, our input is ABI, and the output G. So all our outputs have a confidence. So let's say the output G with a probability of 0.5. So basically, on the output layer here, we get a confidence of that this is supposed to be the next letter or number, and then we normalize that confidence to turn it into a probability distribution. So let's say our probability of having a G is 0.5 as predicted by the network. Probability that the next letter is E might be 0.4, and our probability that the next letter is an L might be 0.1. And then the probability for all other letters might be 0. This is just like a dummy example. So when we generate when we sample from this distribution, let's say we do 100 different samples, then 50 out of 100 are going to be G, 40 out of 100 are going to be E, and 10 out of 100 are going to be L. So that's basically how our generator will work. So this is basically why these language models are called stochastic parrots, basically, because there's some uncertainty in the letter that they're going to choose, and they use, I guess, a probability distribution to choose that letter or word. So that's basically what this generator does here. Is it'll it'll sample from the probability distribution on the output of the network. So the first thing we use is we initialize the network with 3 dots, basically. That's our first input. And then we generate our probabilities from the network, and our probabilities are in a NumPy array, but we want to actually turn this into a torch array so that we can use our generator. So we sample from the distribution using this generator here, and then we add the letter, we append it back to our input, and we drop the first one. So, and then we do that again until we get a dot or a 0. So a dot is indexed by 0. So this is basically do until dot. Okay, so let's run that and we'll see the names. So these are the names here, and some of them look fairly decent. Amari, Tiana, that's a nice one. Lama, Arana, that's a good name. So they're not all perfect, but some of them are actually quite decent. And you can choose what kind of length name you want as well. So in the next scene, I'll show you how to use this for choosing lotto numbers. So we have to adjust the output. We have to massage the output a bit here, because here it ends when we get a dot. But when we have lotto numbers, we want to pick a certain amount of numbers, so 6 or 8 numbers. And also we can't have the same number picked twice in a sequence. So here we've got A and R picked twice, but we can't have that with lotto numbers. So we just have to put in that condition and an ending condition when we've got the right amount of numbers selected. And then in the input, I guess we've got different types where our input is numbers and letters, but that's not hard to adjust. But the network, we don't need to do anything. We can leave that exactly the same as it is now for the lotto numbers, except the only thing we have to change is the vocab size. So I'll show you how to do that in the next scene. This is where I'm getting the lotto history from, this lotto analyzer page, and I'm just scraping it off here with this file here. So this is, I've just written some Python script just to scrape the numbers, and then it generates a file of lotto results. So for Saturday Lotto, we might have this file here. So these are all the numbers. So there's 6 numbers and then a supplementary number at the end. This is the file here. This is the script for scraping it, but put that script on my GitHub repo and you can have a look at that in your own time. I'm not going to go over that, but you know, if too many people are scraping it, they might update this site to make it more difficult to scrape. At the moment it's fairly easy. So there's 3 lottos I'm looking at, which are all the Australian lottos. There's the Saturday Lotto, which is 5 million. There's a Powerball, which ranges anywhere from like 4 million to 100 million. And then there's the Monday, Wednesday Lotto. All right, so let's update this this code here to train on lotto numbers. All right, so let me save this as a different file name. So the first thing I have to change in here is I have to change the file name. So sat lotto. All right, now let's actually reset the kernel as well. All right, so okay, so this is what our inputs look like now. So these are like, I guess, character arrays. So this is basically a string of characters. These aren't actually numbers. So let's see how many we've got. We need to 820. So we need to convert these into, I guess, number arrays. Let's do this. Let's do, and now let's have a look. Okay, so we've gone basically from here character arrays into number arrays. So now we've got, I guess, 45 numbers to choose from. If we look at this lotto, this Saturday Lotto, we've got basically 1 to 45. So plus a starting number. So let's have, let's make our, I guess, our vocabulary like 0 to 45, because 0 can be our starting number. Chars. All right. Okay, so now these are all our numbers. Actually, we don't need this, do we? All right, so 0 is 1, 1 is 2, 2 is 3, and so forth. Actually, let's do this. Let's just do that. There we go. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Okay, so now block size equals 3. Do we want to use 3? Let's try with 3. And then we'll see if anything else works. Okay, data set words. Okay, we're not using words are we, we're using results, because we had to change from character to number, remember? Okay, now let's try this. Oh. Alright, we don't have this dot, remember? Alright. Sometimes you get a few errors. Alright, let's try again. Okay, that seems to work. Alright, now let's have a look at our data. Okay, we don't want to use this join statement. We just want to use this. Okay. Oh. Alright, so let's try this. Alright, so that worked. Okay, so now everything seems to be working fine. So we can just use the network as planned. My seed. Oh no, I didn't set that properly. Alright, let's try this. Okay. Okay, so that's our model there. And we notice now we've got 53,000 parameters, where in the last one we had 50,000, and that's because our vocabulary is slightly larger. We've gone from 27 to 46. All right, so now let's do the fitting, and I'll stop the recording just to make it a bit faster. Actually, it runs pretty fast because we don't have a large data set. Okay, so our loss has been reduced from 3.8 down to 3.15. So in the start, our loss is here at 3.8. So let's have a look at what our 1 on 46 log is. It should be pretty close, 3.8, all right? And okay, and now it's reduced to 3.1. That's about right. So 3.15 is now our loss. So we're getting a better loss. But now let's have a look at the loss in our training set, which is 2.9, which is pretty good. Now this is our development set, which hasn't been used in training at all. 3.19 and 3.16. So that seems a little bit better, 7% and 8% accuracy. Okay. So now we need to update this to generate our actual lotto numbers. Let's just have a look at this first without doing any updating, but let's have a look. If ix equals 0, or let's say equals 6, all right? All right, I might just stop that for now. Stop the recording and I'll do some troubleshooting. All right, so I found the issue. I needed to use length out, not length context, because the length of context is always going to be 3. So let's have a look. Okay. All right, no. Okay, let's just. Okay. Okay, so these are the numbers that we pick. All right. These are the numbers that I've picked for Saturday. And like I said, I'll put all this code up on my GitHub and you can have a play with it. Thanks for watching and bearing with me. And I'll see you in the next video, hopefully.